This video will go into the Nobel Prize in Physics for the year 1906, awarded to Joseph J. Thomson, for his theoretical and experimental investigations on the conduction of electricity by gases. First, a bit longer explanation why he got the prize, coming from the official side. The idea that electricity is transmitted by a tiny particle related to the atom was first forwarded in the 1830s. In the 1890s, J.J. Thomson managed to estimate its magnitude by performing experiments with charged particles in gases. In 1897, he showed that the cathode rays, radiation emitted when a voltage is applied between two metal plates in a glass tube filled with a low-pressure gas, consist of particles, electrons, that conduct electricity. Thomson also concluded that electrons are parts of atoms. Here you see that he also worked with isotopes, and he discovered, I don't know whether he discovered neon isotopes. If you want to know, check it out on Wikipedia, for instance. Some biographical information. Thomson's early interest in atomic structure was reflected in his treatise on the motion of vortex rings, which won him the Adams Prize in 1884. His application of dynamics to physics and chemistry appeared in 1886, and in 1892 he had his notes on recent researches in electricity and magnetism published. This later work covered results obtaining subsequent to the appearance of James Clerk Maxwell's famous treatise, and is often referred as the third volume of Maxwell. Thomson cooperated with Professor J.H. Poynting at a 4-volume textbook of physics, properties and matter, and in 1895 he produced Elements of the Mathematical Theory of Electricity and Magnetism, the 5th edition of which appeared in 1921. In 1896, Thomson visited America to give a course of 4 lectures, which summarized his current research at Princeton. These lectures were subsequently published as The Discharge of Electricity Through Gases. On his return from America, he achieved the most brilliant work of his life, an original study of cathode rays, culminating in the discovery of the electron, which was announced during the course of his evening lecture to the Royal Institution on Friday, April 30th, 1897. His book, Conduction of Electricity Through Gases, published in 1903, was described by Roger Rayleigh as a review of Thomson's great days at the Cavendish Laboratory. A later edition, written in collaboration with his son George, who also won the Nobel Prize later, by the way, appeared in 2 volumes, 1828 and 1933. Thomson returned to America in 1904 to deliver 6 lectures on electricity and matter at Yale University. They contained some important suggestions as to the structure of the atom. He discovered a method for separating different kinds of atoms and molecules by the use of positive rays, and developed by Aston Damter and others towards the discovery of many isotopes. In addition to the just mentioned, he wrote books like The Structure of Light in 1907, The Corpuscular Theory of Matter in 1907 also, Rays of Positive Electricity in 1913, The Electron in Chemistry in 1923, and his autobiography, Recollections and Reflections in 1936, among many other publications. Also, this information summarized by me came from the official site. If you want to read the complete text, you can follow the link. It will also be in the links to the site will also be in the description under the video. Here you see one of the cathode ray tubes he used. It's a version of a Crookes tube. Yeah. And another one. He used this to, as you can read, to demonstrate that cathode rays can be deflected by a magnetic field, and it shows that it's not something like light, for instance. You cannot deflect light in that way. Then from the award ceremony speech by Professor J.P. Claassen, also summarized by me, I think most important parts. The importance of electricity grows every day. The conceptions related to which it are becoming common knowledge. Ørsted discovered the influence of an electric current on a magnetic needle in 1820. Ampere formulated the theory explaining magnetic phenomena as results of electric agencies. Maxwell's work was even more far-reaching. Light was proved to be dependent upon electromagnetic undulatory movements in the ether. The recent discoveries about the discharge of electricity through gases will prove to be important. It's changing our perception of matter. J.J. Thomson has made most valuable contributions through his investigations and researches, which he has assiduously pursued for many years past. Faraday, discovered in 1834, showed that every atom carries an electric charge as large as that of an atom of hydrogen gas, or else a simple multiple of it. There's 2 times, 3 times, 4 times, etc. To speak, as Hellman's, of an electromomentary charge as the quantity of electricity inherent in an atom of hydrogen gas in its chemical combinations. Next page. Yeah, Faraday's law. Yeah, Faraday's law. A gram of hydrogen carries an electric charge of 28,950 times 10 to the 10th. This should be a point, I guess. Yeah, sorry, a little mistake. Electrostatic units. So, if we knew how many hydrogen atoms are in a gram, we could calculate how large a charge there is in an atom. The kinetic gas theory states that gases consist of freely moving molecules, the impact of which is recognizable as the pressure of the gas. We can calculate the velocity of the gas molecules and the volume of space occupied by the molecules, and to form an idea of the mass of the molecules and consequently the number of the number of molecules to be found in 1 gram of a chemical substance. The figures are not yet very accurate. If it was possible to calculate the number of molecules in a drop of water, it might have been otherwise, but it was impossible, and thus the existence of molecules was recognized as problematical. When we calculate how large the quantity of electricity is carried by 1 hydrogen atom, the conclusion is that it lies between 1.3 times 10 to the power minus 10 and 6.1 times 10 to the minus 10th power electrostatical units. This is European, a comma here. In English, I believe it should be point. Sorry for that. We'll get that later. So several other times probably. Hellman found in 1878 that electrically charged small particles possess the property of condensing steam around them. Thomson and Willis observed this phenomenon. Using Röntgen rays, they produced electrical charged particles in air, assuming each particle carries an electric unit charge. By electrical measurements, he determined Thomson, how great the electrical charge was a given quantity of air. Then, by sudden expansion of the air, he effected a condensation of the electrically charged particles. Their size he calculated from the velocity with which they sank. Now, knowing the amount of water condensed and the size of each drop, he calculated the number of drops, being the same as that of particles. Having before determined the total quantity of electricity in the vessel, he could reckon out what quantity there was in every small particle, thus the atomic charge. It was thus to be found 3.4 times 10 until the -10th power electrostatical units, and it's very close to values predicted by the kinetic gas theory, making the determination very probable. Thomson observed the quantity of electricity carried by each atom. Using the number has been determined of the molecules in a cubic centimeter of gas at a temperature of 0 and under the pressure of 1 atmosphere. It's not clear what 0 here means. Celsius? Probably. Then he calculated perhaps the most fundamental constant in the material world, and that number is 40 trillions. 40 times 10 to the 18th power. Thomson and his pupils determined the most important properties, mass and velocity, due to a given force, of these electrical charged particles produced in a gas by Röntgen rays or by Becquerel rays or UV light, or needlepoint discharges on an incandescent metals. There are several ways to produce these rays. The most remarkable of these particles are those constituting the cathode rays in a highly rarefied gas. These particles are called electrons, the object of many investigations like Leonard and Thomson. These particles are to be met with also in beta rays emitted by certain radioactive substances. Thomson's work should carry the negative unit charge but possess about 1,000 times less mass than the atoms of a hydrogen gas. The least positively charged small particles we know are, according to Thomson's, Wien's and other investigations, of the same order in mass as ordinary atoms. All substances are capable of giving off negatively charged electrons. Thomson therefore assumes that the negative charge in the electrons has a real existence, whereas the charge of the positive small particles arises from a neutral atom losing one or more negative atoms with their charges. Thomson has given a physical importance to the 1747 view by Benjamin Franklin that there is only one kind of electricity, also stated by Eklund. The actually existing electricity is negative electricity according to Thomson. In 1892, Thomson showed that a charged body moving forward is thereby in possession of an electromagnetic energy, which produces the effect of the mass of the body being increased. From experiments by Kaufmann regarding the velocity of beta rays from radium, Thomson concluded that the negative electrons do not possess any real but only an apparent mass due to their electric charge. It's reasonable to assume that all matter is built up of negative electrons and that mass in matter was apparent and really dependent on the effect of the electrical forces. An experiment of very great interest has moreover been made in this direction by Thomson, but his investigations of most recent date in the present year, 1906, seem to indicate that only about 1,000th part of the material is due to electric forces. Well, that is something about the so-called electric mass theory. And theory was later abandoned and replaced by the relativity theory of Albert Einstein. But that is at a later date. Here you see some of the theoretical works Thomson did. Here you see how he believed that the electrons in an atom are displayed in what pattern they are. It's the so-called Thomson atom model. Later, of course, it was also replaced by other models. Here you see the same for more different atoms. Here you see 4 atoms. Here you see 5, etc. An interesting theory, by the way. If you want to read about it, you can see that you can go to Wikipedia. Well, this was it for the moment. Next week, we will go into the lecture given by J.C. Thomson for receiving this Nobel Prize. Thank you for watching, and maybe until another time.